license from UPLB. Hindi pa. Pero mukhang hindi nyo naman kailangan, no? Pero kasi yung Outlook credentials, yun yung ginagamit para ma-activate yung UP linked account sa Microsoft Teams. Sa Microsoft Teams kasi, pwede kayong join dun sa AMAT 255 na Teams na ginawa ko for this sem. Ang maganda kasi sa kanya, para siyang Facebook. Pag binaba ko yung call, mag-start yung recording, and minutes after, nandun siya sa thread no meeting for the day. So it looks like this. So, nandito nga pala. So, sa Teams, so meron akong ginawang AMAT 255H na team. Tapos nandito siya, para siyang Facebook page. So may kakita nyo dito yung bawat meeting, and then you can dun sa comment section ng bawat meeting, doon nakalagay yung recording so that I don't need to wait na ma-upload ko siya somewhere. Although ang ginagawa ko naman ay kasi nabubura siya after 60 days yata. And hindi na ako nagtitiwala, naka-record pala ako. Pero anyway, natatakot ako dun sa baka biglang mawala na naman yung Google Drive ng UP. Kasi dati binabaan nila kasi 500 gig tayo usually. So dati ginawa nilang 75, may threat dati na magiging 15. So kaya natatakot na ako sa mga recordings at mga video. Kaya nililipat ko siya sa YouTube para libre yung access, libre yung data storage. So, hindi ko siya kailangan i-keep ng matagal. But anyway, so it could be advantageous if you'll be getting this. Though, yeah. Pero anyway, hindi naman required, pero it would be a good thing to have that. Okay, so for today, we'll just finish this module. I think it's Math 175 module 9, if I'm not mistaken. So last time we were talking about some numerical linear algebra tools that will help us solve tall and skinny matrices, which usually happen in data science. Because again, we are often solving systems of linear equations kung saan ang dami niyang rows kasi bawat row ay nagko-correspond sa isang data set, which will model how the parameters will predict yung data in a particular scenario, in a particular x value, etc. And then at the same time, you want less columns because gusto mo konti lang yung parameters. Kasi pag sobrang dami ng parameters, napaka-komplikado ng model, and at the same time, siya ay overfitted. So na-overfit mo yung data because you're assuming that there exists a certain relationship, masyadong restraining yung model, so wala nang room for interpretation. Na baka naman may iba pa kasing pattern na mag-exist between the data. So that's why we want a simplified model, but not oversimplified na wala ka nang nagigay na information. So you want to strike always a balance, but always at the end of the day, data science and usually other inverse problems tools or techniques ay nangangailangan ay nagsosolve ng tall and skinny matrices. Which reminds me, on November, kailan nga yan? Sometime mid-November, I think it's November 17 and 18, baka magkaroon ng mini research workshop, 2-day research workshop here in UPLB. So you might be interested. I don't know, 17, 18? That's Friday and Saturday. Friday and Saturday. So 17 and 18. It is the mini school is titled Deterministic and Theoretical Tools for the Data-Enabled Sciences. So if you want, free naman yun. So if you want, just tell me. Maglalabas din kami ng invitation soon, hopefully next week, and then I can send it to you. So if you are interested. So dito lang din naman yung gaganapin. So kung nandito lang naman kayo at wala masyadong gagawin, baka mag-cancel pa ako ng klase nun. Ay, hindi na pala ako yung teacher nyo dito by that time. So, libre na ako ng Friday na yun. But anyway, if you are free, you're encouraged to join. But anyway, so we were talking about tall and skinny matrices, which obviously are not square, and hence they will not have inverses. That's why we have to look at tools that will allow rectangular systems. and in general, systems that are characterized by non-invertible coefficient matrices, right? And we bumped into what we call the Moore-Penrose pseudo-inverse, which basically tries to generalizes the concept of an inverse in the sense that you want all matrices, be it square, be it non-square, to have inverses, and at the same time, you want to keep the inverse of the invertible matrices. In other words, you want the pseudo-inverse of an invertible matrix to be its inverse right away. And I think I presented the definition last time. The pseudo-inverse is the unique matrix A plus that will satisfy all of these four conditions, right? And I think nagtapos tayo dun sa pagkuha ng paraan kung paano ma-solve ang gulo na ng notes ko, pero kung paano ma-solve ang pseudo-inverse ng isang matrix, at least by hand, right? Because the definition tells us what are its characterizing properties, but we don't know how to construct the pseudo-inverse. But essentially, if these two very cheap conditions, I mean, these are very easy conditions are met, then the pseudo-inverse can be computed accordingly, right? So usually it's the first condition, nag-apply yan, usually, lalo na kung natural phenomenon yung problem, chances are A conjugate transpose times A will be invertible. And of course, later I'll show you how to ask MATLAB to compute the pseudo-inverse for us and what are the implications of pseudo-inverses. So for today, our goal is to finish this up, show a quick example of how the pseudo-inverse play in terms of solving linear systems. Though hindi ako magko-consider ng napakalaking linear system, that's for you to work on in the second problem set. Pero mga baby problems yung papakita ko sa inyo. And then hopefully we can also go to the L-curve technique later, which is another very useful tool from linear algebra in the data sciences and actually even any physical science or any modeling problem that requires solving very large systems. So yun yung objective natin for today. So let's see ano yung saan natin simulan. Well, so as I've mentioned, we'll be looking at paano pumapasok sa picture yung pseudo-inverse in terms of solving the linear system. Now we start with the equation or the system AX equals B. And then it can be proven, although hindi ko na siya usually pinapakita in the undergraduate courses, that any solution of system 9.2, if they exist, will be of the form 9.3. It will be A pseudo-inverse times B plus this guy. Identity minus A pseudo-inverse times A times a vector W. And the vector W here is any vector of the correct dimension. So yung sinasabi niya. Kapag ka si X, kung etong system na to ay may solution, right? Be it a unique solution, be it an infinity of solutions, then we are sure that its solutions will be of the form of equation 9.3, right? Now, there was a good question last time. I think Gio asked, lagi ba yung alin identity yung pinag-workan? Well, it would be A pseudo-inverse times A usually becomes an identity of the appropriate size. But that's not always the case. Hindi siya laging nagiging identity, pero dapat yung A conjugate, satisfy pa rin yung apat na conditions nung pseudo-inverse, right? Now, kapag ka ang A pseudo-inverse times A ay eksaktong equal sa identity, then the system 9.2, yung AX equals B, will have a unique solution, right? Because again, if A pseudo-inverse times A is equal to identity, so this guy will become the zero matrix times a vector W, so that will just be zero. So you'll be left with the unique solution A conjugate transpose, A pseudo-inverse times B. Yun yung makukuha nating solution. However, kapag ka yung A pseudo-inverse times A ay hindi eksaktong identity matrix, so the identity matrix times A pseudo-inverse times A is a non-zero matrix. And then W here can stand for any vector of any size. So that means this is non-zero. You get an arbitrary vector W of the correct size, multiply them up, add them to A conjugate A pseudo inverse B, then you will get another X that solves system 9.2. That's why, or that's how the pseudo inverse captures all of the solutions to an over or an underdetermined system. Kasi nga, kapag ka hindi square yung matrix, or in particular, hindi invertible yung matrix A, then yung equation 9.2 will have infinitely many solutions. The pseudo inverse can capture all of those solutions via this form. Okay, so I think I have an example that shows that here. Right? Kaya lang, so makukonsider natin kapag ka meron kang unique solution, pag yung equation 9.2 ay may unique solution, kapag ka meron siyang infinity of solutions, maka-capture siya ng 9.3. Next question is, sir, paano kapag ka walang exactong solution, right? Because those are the three the three possibilities. Well, kapag ka si equation 9.2 ay walang exactong solution, ang binibigay ng pseudo inverse ay yung solution na may pinakamaliit na residual. When we say residual, that is AX minus B, or the size of AX minus B. Yung AX minus B, siya yung residual. So pag walang exactong solution, yung AX equals B, ang hinahanap ko ay yung next best thing to a solution, and I call it X star. How can we say that it is the next best thing to becoming a solution? Well, kunin mo yung AX star minus B, and you want it to be as small as possible, right? Because you're solving AX equals B, so kung yung AX star ay malapit sa B, then X star would be a good pseudo solution, or a good approximate solution, right? Kung wala talagang solution, edi hanapin natin yung pinakamalapit na maging solution. And how do we define pinakamalapit? Well, we look at the size of the residual. So you multiply A by your purported solution X star, subtract it from B, that's your residual. Yun yung natitira. And you get the norm or the size of that residual, then that will give you the idea of how far away is your solution from the action, right? However, usually, I think nasabi ko na to sa inyo dati na when you compute the residual, you will have an idea how big the error is, right? Yung absolute magnitude ng error. But with respect to what, hindi natin alam. So that's why instead of just the residual, I want to look at the relative residual. So the relative residual would be just the residual of the norm of the residual. Kunin niyo yung norm ng residual divided by yung norm ng right-hand side. So this will sort of give you the percentage error. So we can call it the relative residual norm. So pag divide mo yung size ng residual by the size of whatever you are approximating, then that will give you the percentage error. And I think that's a better measure of the a better measure of the goodness of your solution rather than just the residual norm. Right? Yes.
Sir, yung sa naipunin ko kasi, pwede nasa ang idea of the construct as pero kung siya natin is bigay ko sa invertible or yung isa invertible, paano kung wala akong invertible sa dalawa?
Well, may ibang algorithms, kaya lang hindi siya ganun ka-simple. Right? So, ito yung nasa theorem, I think that was 9.3. Siya yung pinakamadaling gawin. And usually, that they are sufficient. Pag hindi, well, hanap tayo ng ibang algorithm. So, yeah, actually, that's a good question. Paano siya?
Kasi, yung algorithm is through the code na yan, sir.
Yeah.
And by solving by hand, wala.
Meron pa siguro. Hindi lang ako familiar doon kasi lagi lang na ito na yung kailangan. At kapag saka hindi kasi ako nagsisolve by hand. But that's a good question, right? And actually, yeah. Maraming methods ng pag-adjust tayo. Kailang hindi na siya worth it. Kung kaya naman siya ng computer, then why not? But this, for starters, you look at the most basic ways to derive those things, right? Okay, so yeah. So kinukuha natin, so if there is no solution to system 9.2, you're looking for the one that will minimize the residual norm. Minimize na lang natin yung residual norm because that's equivalent to minimizing the relative residual norm. Kasi scalar multiplier lang naman yung 1 over absolute value B or norm B. Kaya lang, if you will be describing the accuracy of your solution, it's better to talk in relative terms or percent terms rather than the sheer magnitude of the residual, right? But in any case, it turns out that the minimizer of the residual with respect to the L2 norm is incidentally given by the pseudo-inverse. So there might be different algorithms on how to find the next best thing to a solution. Kasi itong nandito ay generic residual norm. You can, I'm sure you're familiar with L1 norm, L2 norm, LP norm, ano pa ba mga klaseng norms, and different norms, right? Nakadepende kung paano mo susukatin ang isang bagay. Depende sa norm or sa measure na gagamitin mo. So it depends on the measure that the norm that you will use. But if you're talking about the L2 norm, yung pseudo-inverse, incidentally, ang makakapagbigay ng minimal residual. Right? So that's why we want this guy because this minimizes the L2 norm of the residual. Of all the x's in the space of all n by 1 matrices, yung x star given by the A pseudo inverse times B will minimize this L2. Right? If your norm is different from L2, it might not be the pseudo inverse. The pseudo inverse might not give you the best residual or the smallest residual. But usually we are interested in the L2 norm kasi siya yung usual extension ng L2 distance. Pero minsan taxicab distance, taxicab norm L1, L infinity. So depende sa gagamitin nyo. Probably you might, if you're interested in other kinds of norms, you might need some optimization tools. Pero pag L2, hindi na kailangan natin ng autonomous na optimization solver kasi pseudo-inverse na kagad yung makakapagbigay nun. Right? Okay. And actually, ito ring pseudo-inverse coincides with the normal solution. I don't know if you have heard of the normal solution na siya rin yung least square solution. So, which is the usual trick, especially when working with non-square matrices. Or actually, ginagamit din to when solving generic systems. So for instance, we start with the equation 9.2 ulit, AX equals B. Then using multiplication property of equality, I can multiply both sides of the equation by the conjugate transpose of A. I will get this. And if this guy, of course, associativity is factored in everywhere here, right? Kaya nakapag-regroup ako ng matrices. So pag ginroup ko itong dalawa, right? And this happens to be invertible, then I can multiply both sides of the equation by the inverse of A conjugate transpose A, and I'll get the value of X, which is this guy. And note that since here I am assuming that this guy is invertible, so kaya ako nagawa to, but if you notice, this product is indeed the pseudo-inverse. So kaya ang least square solution sa isang rectangular system o sa isang non-invertible system is given by a pseudo-inverse times. Right? So which is another nice property of the Moore-Penrose pseudo-inverse. Right? So I think that's all that I want to show here insofar as the pseudo-inverse is concerned. I think the rest you can read in the module kasi solution by hand lang yung pinakita sa module. Pero pwede naman natin siyang padaanan, ano? Pero mas gusto kong ipakita yung MATLAB implementation niya kasi you'll be working with large matrices later. Baka hindi na relevant para sa inyo yung hand solution, ano? Pero in this example, I need to correct something here. Let's see. Yeah, mali itong householder transformation. Na-discover ko lang kanina, typo itong minus 5.625. Hindi pala typo, mali yata yung napindot ko sa calculator when I'm writing this. So hindi negative 5.625 to. And by the way, this is the solution from QR factorization. If you're interested with QR factorization, because I might not have the time to discuss it, I send you a link. I sent you a link kanina for QR factorization, some notes on QR factorization. And I think it was example 65.m, which is the MATLAB implementation ng examples dun sa modules at dun sa reporting, if you want to recreate those things. If you became interested with that, you can set a consultation with me para pag-usapan natin yan. Pero hindi ko na siya kasi masisingit in the actual class, right? So, but what I want to point out here is here in the second part of the solution, right? Now, pinakita niyo yung step-by-step computation ng A pseudo inverse. Kinuha yung A conjugate transpose A. Tapos kita na siya ay invertible. Tapos kinonstruct yung A pseudo inverse. And X star was computed to be A pseudo inverse times the right-hand side B, right? And then you will get this. And actually, this is also what you'll get when you use the householder QR decomposition. Kaya ko na-discover equal lang pala sila. I don't know what happened when I wrote this modules, no? Kamali siguro ako ng pindot kay MATLAB or something. But this is the next best thing to a solution that we can get. Why do I know that this is the best thing with respect to the L2 norm? Kasi hindi siya yung exactong solution. Because if you check AX star, times this guy, right? So, ang makukuha nyo ay, actually, sige, pakita ko na lang mamaya sa MATLAB, hindi siya yung right-hand side na vector 2461. Hindi mo to makukuha. Actually, 2461, this vector is not in the range of the matrix A. Wala siya dun sa lahat ng possible products of a vector times A. Kaya wala kang solution, right? But the next best thing to a solution that you will get is guaranteed to be this one, right? But unfortunately, ang layo niya, hindi siya malapit hindi niya mabibigay yung 2461 ng malapit. Because if you compute for the residual, you will see that the relative residual is 0.4636. So that means it's 46% off from the vector 2461, which is not good. That's actually very bad. Pero the theory suggests this is the next best thing that we can get. Ang ibig niya lang sabihin, ang layo ng vector B 2461 mula dun sa range ng matrix na A. So ito na yung pinakamalapit with respect to the Euclidean distance that we can get. Right? So maybe maybe let's jump to MATLAB and see how this is implemented. Right? How's the MATLAB? Pasamihan natin yung MATLAB demo. So okay. So I started typing it kanina. So I have here A. I'll just copy paste it here. Okay. Now in this line, in-encode ko lang yung matrix na nandun sa module. Oh, sorry. Ito. Okay. Wait, ano nangyari? Tagal ko pala nagsasalita kanina. Ang naka-project ay yung tama. Ano naka-project kanina? Naka-project kanina ba yung notes?
Yes.
Bakit bigla nag-MATLAB? Napindot ko na ba yung yung palit ako ng okay. Yeah. Okay, sa projector pala siya. Sorry naman. Nalito ako. Pero kailangan ko itong i-share para lumabas siya sa recording. Okay, so yan. Kasi pag hindi ko siya shinare, hindi ko siya makita sa recording. Although, hindi pa rin yata siya makita. So, ang hirap ng online, nagiging ikaw na yung artista, ikaw na yung director, ikaw pa yung cameraman. Ano? So, like, hold on. Yeah, naewan ako. Pero siguro 2 semesters ago, gamay na gamay ko na to. Pero biglang nag-face-to-face tayo. So, yeah. Okay. So, yeah, I think we can see now online. Okay, now, So tinype ko yung matrix A na nandun sa module, right? So 2, 4. Now in MATLAB, when you're encoding matrices, yung spaces, siya yung nagsiseparate sa columns. Tapos yung semicolon, yung magdadala sa'yo sa panibagong row. So if you have a copy of the notes, dun sa example natin, ang first row ay -1, -1, 1. So tinype ko lang siya -1 space -1 space 1, and then para mapupunta ako sa next row, nag-semicolon ako. So that's how I got the matrix A. And then the matrix B, dahil siya ay column vector, 2, colon 4, colon 6, colon 1, right? So you can highlight this, press F9 para ma-load it, para ma-solve to without saving the file, right? Kasi pagka nag-highlight ka, right-click, evaluate selection, talagang ipa-perform nyo lang yung commands na highlight mo. Or you can highlight everything and then press F. Or if you want to write it as a code na isa-save mo later, i-save mo siya as a example. Lagyan mo ng file name. Tapos you can press F5 para mag-run yung entire thing, right? Kung sure ka na, or you can press the run button. Run button o kaya F5. So it will run the entire save program. So ang problema lang ay kapag ka nagde-debug, usually pag may mali sa code mo, ayaw mong i-run ng buo. Gusto mo siyang i-run section by section, line by line. Kaya maganda rin yung nag-EF9 o yung nag-highlight and evaluate selected selection, right? Now, you will see on the right panel that I have the workspace populated by A and B. So if you want to check, you can type A on the command window, lalabas na yung matrix A. Tapos type mo yung B sa command window, you will see the matrix B. So pag meron kang set of instructions, dun mo siya itatype sa editor, dun sa taas. Kapag gusto mo siyang parang calculator na you come and go, so pwede rin din dun sa command window ka magpa-compute. Now, all of the variables that you declare either in the editor or in the command window will go into the workspace. Makikita mo siya dito sa panel. And then you can call them anytime you need it. Now, there are several ways to compute the pseudo-inverse, right? Hindi ko naman kailangan yung pseudo-inverse, so dito ko na lang ipakita kung paano siya kinocompute. PINV, yung syntax para sa pseudo-inverse. So if you want to get the pseudo-inverse of A, you type PINV of A, then you press enter. This is the pseudo-inverse. And I think this is what is shown in the handouts. That's the pseudo-inverse that you will get, right? And then remember, sabi natin yung X star. So lagay ko siya dito sa ating document. Ang X star natin ay yung least square solution ay pseudo-inverse ni A times the right-hand side vector B, right? Now the semicolon at the end of the lines will just tell MATLAB do not display the answer of that line or the result of that line. Kasi otherwise, lahat makikita ko dito sa command window. Pag meron naman mga intermediate computations na hindi naman ako interesado sa itsura ng solution, hindi ko na siya ipapadisplay to save time and presentation-wise, right? So nakatago na siya dun sa keychain. Now, hindi ko naglagay ng semicolon dun sa X star sa line 4 because I want to see X star in the command window displayed, right? So if I press F5, automatic magsisave yung file at irarun niya yung command, right? So you see here that X star is -635, 375, 2.75, and 0.125. And then if you're curious, is this an exact solution? Pwede mong ipa-compute kay MATLAB dahil ano lang naman to off the top of my head computation. Hindi siya importante pero sanity check kumbaga. You want to check if I got a good solution, kunin mo yung A times X star. So this will tell us dapat ang sagot ay malapit kay B, tama? Dapat malapit kay B. But if you enter, you hit enter, you'll get 3.75, 225, 425, 2.75, but I'm expecting 2461. So super layo na talaga. So kung gusto mo lang tingnan malapit ba hindi, mukhang malayo siya. But in order to get an idea how malayo siya from the solution, then kunin mo yung dapat pala pinangalanan ko na to. kunin mo yung AX star minus B para makita mo gaano sila kalayo mula sa isa't isa, right? So ang difference between what we get with what we tried to mimic or to target is ito. 1.75, sorry, minus 175 minus 175, 1.75. Ito yung residual vector. Ito yung difference ng AX star mula kay B. But of course, this doesn't have any nice interpretation. Gusto kong makita ano yung size niya, right? Isang shortcut pala kay MATLAB sa command window, you can press up para ma-display yung mga recently used commands. And then, kunin ko na lang yung norm ng AX star minus B to give me a single number that will give me an idea how big the residual is, right? If you just type norm, ang default ni MATLAB ay L2 norm. So ang L2 norm ng residual ay 3.5. So meaning, ang size ng residual ay around 3.5. But you see the difficulty here, I don't know, is 3.5 a good number or is it a bad number, right? So para malaman nyo kung is it a good number or a not so good number, it should be compared to the target, the size of the target. So ito na yung relative residual na gusto kong pagpitin. I will divide it by the norm of the target B. Right? And then this will show me 0.46, which we have seen in the handout, right? So 46% yung error. Ang laki ng error kasi yung size ng residual na 3.5 is about 46% of the size of the target vector B. So malayo siya. Pero theory suggests ito na yung pinakamalapit na pwede nating makuha, right? Now, ayan yung pseudo-inverse, pero may shortcut kasi kay MATLAB. Kay MATLAB pala, pwede yung cursor ilagay mo sa isang line, tapos pindutin mo tong percent symbol, magiging comment na lang siya. Pag comment siya, hindi siya babasahin ni MATLAB. Usually, this is something a programmer use in order to label ano yung ginagawa ng bawat line. So, hindi yung kukumpitin ni MATLAB para yung sa nagbabasa. Or kung ayaw mo lang i-run yung certain part ng code. Now, a shortcut to using pinv ay a/b. Right? And it is the same as pinv times p. It's just that yung backslash, it will tell MATLAB to find the easiest way on how to come up with a pseudo-inverse or how to get the least square solution. Kasi hindi lang pseudo-inverse yung hindi lang siya yung paraan para makuha yung least square solution. Pero meron pang ibang algorithm na posibleng mas mabilis via the pseudo-inverse, yun yung ginagawa ng backslash, right? So if you run this with the backslash thing, ibibigay niya uli sa atin ay the same X star negative, which we already saw in the previous example, right? Now, actually, kahit invertible symmetric sa A, dinidiscourage ni MATLAB yung users to use X star equals inv of A times B. Kasi mahal nga yung pagko-compute ng inverse. MATLAB suggests users to use A backslash B, right? Kasi anyway,
Pero inside verse na rin.
yes, dapat hindi magka-coincide ng wala kasing konsepto ng inverse dito sa A backslash B, pero yung solution na makukuha mo ay parehas. Kasi yung A backslash B, ang ginagawa niya, hinahanap niya yung least square solution. So kung may nag-exist na unique solution or may nag-exist na solution, siya na yung least square solution kasi yung size ng residual niya ay 0. Tatapatan yon ng A backslash. Maghahanap din siya ng least square solution. At kung nag-exist yung least square solution at equal kay 0 yung residual norm, yun din yung ibibigay ni backslash. Kaya suggested, backslash yung gamitin nyo, wag inversion kay MATLAB. Right? Dini-discourage ni MATLAB actually yung inversion, especially for ill-conditioned matrices. Mas stable yung backslash. Okay. Yeah, I think that's what I want to show here. Let me see. Okay, another example siguro. And this is example 9.2 in the handout. Pero gawin natin siya kay MATLAB. So na ko yung i-recreate ko yung discussion dun sa module. Now I have here a 3x2 matrix. Copyin ko siya, tawagin ko siyang matrix A. So 0.15. I think I have that here. Copy paste ko na yata here. No, here. Where? I think I have that here. Palitan ko lang yung A and B. Gamitin kong A ay 0.15, 0.1, 0.161, 2.02, hanggang 1.3, and then 0.95, 2.2. Okay. So I just changed A and B, same code for X star. Then if I press F5, I'll get X star equals 1, 1. Right? See, so nakahanap ako ng solution. Okay. And then what I'll do here is check if I got an exact solution. I don't know kasi kung this is an exact solution or is it just a next best thing to a solution, right? So to know that, I'll just multiply A and X star, or I can compute for the residual, right? O kaya kung gusto nyo, maglagay na kayo dito na relative residual, ano ba? Rel residual. So rel residual lang yung variable na itatawag ko. So arbitrary yung pagkakapangalan. So pwede kayong mag-isip na ibang variable kung anong itatawag sa kanya. Gusto ko lang siyang tawaging relative residual para mas madaling tandaan. And this is the norm of A times X star minus B, tas relative residual to, so divided by the norm of B. Right? Para malaman ko yung percent error. Right? Then if I press F5, so nakuha kong X star, 1, 1 as before, but meron siyang additional na display, yung relative residual ay 1.64 times 10 to the minus 16. Now in MATLAB, any number of the order 10 to the minus 16 can be treated to be 0. Meron na mga numerical artifacts na involved, right? So yeah, so I am thinking I might have bumped into a exact solution. Actually, pwede natin siyang matest. Pwedeng 8 times. Ang solution natin nakuha ay 1, 1. You'll see it's 0.25, 0.26, 3.32, exactly P. So meron tayong exact solution. Question is, do we have a unique solution? Baka naman may iba pang solution X star, right? Now, if you will go back to the notes, meron dong sinabi, tingnan ko kung kaya kong mag-annotate. Why? Hindi ako pwede mag-annotate. Pero dun sa slide, sa equation 9.3 dun sa handout, it gives us all of the solutions, right? And as I've mentioned earlier, the existence of an infinitude of solution hinges on A pseudo-inverse times A. Kung yun ay identity matrix, unique solution. Kung hindi siya identity matrix, then magkakaroon tayo ng parametric solution with respect to a vector W of the appropriate size, right? Pero pag kinuha ko yung P-in ni A, kasi names ko siya kay A, makukuha ko ay identity matrix. So dahil identity matrix yung A pseudo-inverse times A, yung equation 9.3, magzi-zero yung nakamultiply kay W, unique yung solution. So we have bumped into a unique solution. Even if A is non-invertible. Kasi pag ang solution mo ay inverse of A times B, magreklamo si MATLAB. Kasi walang inverse, kasi hindi square yung matrix, right? But the pseudo-inverse will give us the solution, the exact solution, right? Via the backslash command. Pwede ring P-inf times P. So highlight ko yan, tapos mag-press ako ng F9, 1, 1, makikita ko. So same thing, right? Pero mas efficient kasi yung backslash algorithm ni MATLAB, right? So that's that. Sir, sige.
Dahil pa yung sa yung kailangan ng P-in sa box order, may distinction ba sa nasa?
Wala silang distinction.
Same.
Yeah, so pag nag-solve ka ng linear system, gamitin mo na yung backslash. Kasi kahit ano yung size ni A, mag-work to. Kahit ano pa si A, mag-work siya. Kasi ginagamit niya yung pseudo-inverse times A. Pero yung pseudo-inverse of A, yung P-inv of A, specific yung algorithm. Yung backslash, si MATLAB pinipili sa library of algorithms niya paano mahanap yung pseudo-inverse. That na pinakamadali for the given matrix A. Matalino kasi si MATLAB eh. Siya na nag-iisip ano yung pinakamadaling paraan para ma-compute yung pseudo-inverse. So, posibleng iba yun dun sa P-inv algorithm. Pero if you want to see what's the pseudo-inverse is, P-inv yung tanging paraan. So, kaya kailangan mo siyang i-hardcode. Right? Pero kung di mo naman kailangan yung P-inv, solution lang talaga yung kailangan mo, backslash na yung gamitin mo.
So, for this is backslash.
Yes. Kung hindi mo kailangan makita yung pseudo-inverse. Pag gusto mo lang talaga yung X-star, backslash na lang. Pag binasa mo yung documentation ni MATLAB, sabi niya, huwag kang gumamit ng inverse. Huwag kang gumamit ng P-inv. Gamitin mo, parang awa mo na backslash. Kasi para madali yung computation sa kanya. Para may freedom siya to choose ano yung pinakamagandang solution. So, ganun kaganda si MATLAB.
Sa answer din sa learners, may threshold ba yun na parang okay na para magandang image?
Good question.
Kasi hindi naman natin.
Yeah. Iba-iba. Nung master's at saka nung undergrad, pure math ako. So, tayong mga pure math, hindi tayo nakakontento sa 10 to the minus 8 na relative error. Gusto natin ay almost zero talaga yung error. 10 to the minus 16, 10 to the minus 20. Kaya nung nag-applied math ako, pag nagsasimulate kami ng sound, ng electromagnetic waves, ang engineers, masaya na sila sa 10% na error. Which is, masashock ka, culture shock ka na, 10%, ang laki nun. Pero sa engineers, okay na sa kanila yung 10% error. 5% error is good. So it depends on application to application. If it's a medical application, halimbawa, solve mo yung X-star, si X-star yung magre-represent ng coordinates kung saan katuturukan, well, gusto mo yung residual norm ay mga below 1% kung maaari. Kasi pag 10%, dito ka dapat turukan, dito ka naturukan, so may mga komplikasyon. So it varies application from application. But if it's like structural engineering, nagtatayo ka ng building, plus or minus 5%, plus or minus 10% is still good. So it depends. It varies application to application. In data science, siguro 10% is still acceptable. 15% still acceptable for algorithms, right? Pero ang target mo mga 5% lang yung error. That's an excellent algorithm. But if it will work 80% of the times, then it's considered good na rin. So walang rule of thumb, right? Pag pure math meron, zero dapat yung error. Pero otherwise, we're happy with some errors, right? Okay, so where am I? Sige. Yeah. Tingnan nga natin to. Hindi ko pa to na-try, pero let's freelance a little bit here. Sige, i-ano ko lang tong A. I-comment ko lang siya kasi yung A at saka B. Papalitan ko lang sila. So ang gawin kong A ay nasa example 9.3. 1, 1, 1 ang first row. Second row ay 1, 1, 2. Tapos ang B ay 1, 3. 1, colon 3. Okay. Tingnan ko nga kung ano ibibigay ito. I'll press F5. Okay. It will give me the solution X are 0, negative 1, 2. 0, negative 1, and 2. Now, if I want to see if I have, and then look at the error. Ito pala. 3.51 times 10 to the minus 16. So it seems that I bumped into an exact solution, right? Hindi siya nagsi-zero kasi itong negative 1 na to, baka hindi siya exactong negative 1 na nakasave sa memory. Kasi we are using a finite machine, nagta-truncate siya somewhere. Kung gusto nyo i-check, pwede nating puntahan, pwede nyo i-click yung X-star sa workspace. Double-click nyo siya. Lalabas tong variable na to. Makikita nyo yung kung saan nakasave yung variable without displaying it in the command window. Nag-create lang siya ng additional tab sa tabi ng editor. So, din-display nyo yung data. Pagka nag-double click ka rito, kita mo kung ilang decimal places siya. At nandun sa dulo, may 2 pa sa dulo. And that could be, or that is actually a artifact from the rounding, the truncation that is done in the machine. Kasi sa machines, every operation nagre-round off siya. Say to the 16 decimal places, hindi niya kasi nagtitipid siya ng memory. So hindi niya kina-capture lahat ng decimal places. Pag nag-divide ka, maraming decimal places yan. Kahit nga rational number na repeating, nagmamatter pa rin yung kabuuan ng sequence of decimal points, right? Or numbers after the decimal points. But the computer will truncate that after every operation. Mag-round up siya after niya mag-add bago niya gawin yung susunod na operation, after which mag-round off na naman siya, mag-round off siya every after operation. May mga nawawala hanggang sa dulo bago ka makakarating. Kaya instead na 1, tinatong nakita ko rito, meron pa siyang 2 sa dulo. Right? Now, but I am thinking, well, this could be 0, -1, 2 easily, right? So ang gawin ko nga, try ko nga yung A times yung eksakto na 8 times yung eksaktong 0, -1, 2. And you will get exactly 1, 3. Pag eksakto yung number, hindi naglalagay ng 0.000 si MATLAB. So, katulad nito, 1, 3 yung sagot niya kasi sure si MATLAB na eksaktong 1, 3. Pero kanina na nagpa-multiply ako, -0, -1.000, ibig sabihin, alam ni MATLAB hindi to eksaktong 0. There's some decimal digits after it. Maybe on the 20th decimal place, 30th decimal place, pero hindi siya exact. Pero since 1, 3 is exactly the right-hand side, so I guess we bumped into an exact solution. So yung pseudo-inverse ni A times the right-hand side B ay equal kay 1, 3. Right? And then we check, meron pa bang ibang solution? Right? Yun yung gusto natin makita. Well, paano nga natin titingnan? Titingnan natin yung pinf. Yung pa pala pwede. Mag-type ka ng first few characters, tapos pwede ka mag-up para ilabas si MATLAB yung recent na nag-start sa pina-command na niran ko. Para makatipid ng kaka-type. So yun yung maganda naman sa command window. Quick calculations pwede mong gawin sa command window. Then here, I'll get, sorry, not pinf A, sorry. I want pinf times A. And this is not the identity matrix. Dahil hindi siya identity matrix, hindi unique yung solution, right? How do we get a solution? Go to equation 9.3. The equation 9.3, any solution will be of the form, where was that? Any solution will be of the form, sorry, may see yung memory ko. So, tawagin ko siyang xx equals sa pseudo-inverse times A times B plus quantity. Need to be careful with the grouping symbols. Ang identity matrix kay MATLAB ay I. Mata. Sounds like I identity. Medyo maloko yung mga nagpapangalan sa MATLAB. Ano? Then, kailangan meron siyang argument I of 3. Identity na 3 by 2. So I of 3 minus pinf of A times A times whatever vector W that you want para makapag-generate ka pa ng ibang solution. Well, what is the size of the vector na dapat natin gamitin? It should be 3 by 1. Tama? 3 by 1 siya dapat. So if you type 1, 1, 1, right? Just to get a feeling of how the solutions look like. So this is another solution. -0.5, -0.5, 2. If you want to check if it is indeed another solution, computin mo lang yung norm. Computin mo yung residual ng norm. Yung norm ng residual. So it's a norm ng A times XX. Oh, bakit hindi? Pinf times B plus identity minus P in times A times any identity vector of the right size. Bakit hindi ko nakakuha yung, sorry. Minus B. Namuto ko yung minus B. Naban ako doon. Yeah, 4.4 times 10 to the minus 16. Order 10 to the minus 16, probably this is 0. Right? Kung gusto nyo talagang makasigurado na siya ay hindi equal kay 0, type niyo yung XX as is. Yung XX na na-compute natin kanina ay negative 0.5, negative 0.52, pero they were followed by a series of zeros. That means in the memory of MATLAB, hindi sila eksaktong negative 1/2, negative 1/2 at 2. So ito-type ko siya hardcode ko siya na minus 0.5, minus 0.5. Tapos ano yung dulo? 2 nga ba yung dulo? Yes. Then you'll get 0. Right? May mga numerical artifacts lang na nangyari, kaya hindi nakuha ni MATLAB na eksaktong 0. Bakit nagkaganon? Kasi nakuha natin si XX by computing the pseudo-inverse. May inversion na nangyari kay pseudo-inverse, doon nag-pile up yung numerical artifacts. So kaya yun ang hirap sa applied math o sa numerical simulations. Problema mo na yung theoretical part, kailangan mo pang intindihan ano kaya yung nangyari sa loob ng computer. Right? So kaya ganon kaya it's a field on its own ng numerical analysis. How you will control a computer to behave as if it's a natural solver or a human solver that does everything almost by hand. But of course, imposible yun. They are finite machines. Kaya kailangan pag-aralan paano mo siya paglalaruan or paano mo siya i-modify, right? So yeah, so that's how you see that there are different solutions, and then you just vary yung vector A mo, yung vector W. You can change it to say 8. Pwede mo siyang gawing pi. Para pi ay pi lang. Then you'll get a solution. But it turns out this is the same as what we had before, right? Kasi baka nag-0 siya doon, so gawin ko rito 1, yung gitna kayang gawin kong pi. There we go, you get a different solution, right? But you can do this for any vector W. It's guaranteed that you will get another solution after this. Yeah, you'll get all solutions using formula 9.3. Okay. 3/1. So hindi mo siya na semicolon. Yeah. Kasi maging undefined yung matrix multiplication. So, naging 4/1. Yeah, nagreklamo siya. Error using the multiplication command. Tapos sabihin niya, papagalitan ka niya, incorrect dimensions for matrix multiplication. So you'll know where you messed up. Kasi detalyado siya magsabi ng error. Kung hindi ka pa nasayahan or hindi ka pa nakaintindi, well, merong related documentation na pwede mong i-click. So lalabas yung MATLAB help section. So and then you can also do this even if you are offline. Tuturuan ka niya, ganito mag-multiply ng matrix. Kailangan nagmamatch yung dimensions. So that's why I guess this is a very user-friendly software. Kasi ang ganda ng documentation niya, nag-explain siya kung ano yung posibleng mali. So you know what to expect. And then pagka napuno ka na, ang dami ng pagalit sa ni MATLAB, you can write on the command window CLC para ma-clear yung command window. Mawawala na lahat ng na-compute mo before. Yung workspace, nandun pa rin. Nandun pa rin yung workspace. Nandun pa rin yung history. You can press up and down para sa recent commands. Talagang binuran niya lang yung nasa Blackboard, so to speak, right? Kung gusto mo mawala yung nasa workspace, ang command ay clear. And then you see everything in the workspace is gone. Here yung gagamitin. Hindi na siya? Hindi na. I-run mo na uli yung code. So be careful when you clear, right? Pag nag-type ako ng A, kung hindi ko na clear, nag-type ako ng A, ipapakita niya yung A. Pero ayan, i-reclam siya, unrecognized function or variable A. Kasi wala sa workspace. Na-clear mo na yung workspace. Okay, so what else do I want to say about this? Okay, now, yeah, so that's how we usually solve our rectangular systems. Kaya lang, hindi doon natatapos yung istorya. Ito yung lagi ko sinasabi because I'm doing it in numerical analysis. Meron kang problem na mahirap i-solve by hand o inconvenient i-solve by hand, kaya hingi tayo ng saklolo sa computers. Tapos mukhang maayos na ang lahat, may solution na, tapos bigla ko silang bibigyan ng additional problem. Na paano kapag kaganto? Makita nyo, hindi na mag-work yung program. Isip tayo ng paraan paano ma-solve yun. So parang ganito rin. So nagsimula tayo sa problem of solving rectangular systems, right? Kasi ito, parang meron na tayong magandang solution. Meron na tayong pseudo-inverse na madali siyang computin kahit hindi rectangular yung matrix A. Nakaka-capture niya pag unique yung solution. Pag infinity many solution, kaya natin kunin. Pag walang solution, it will give us the next best thing to a solution, which is the least square solution or the L2 solution. Right? Kaya lang, okay, the solving system, good, pero merong mga pasaway na mga systems na matrices. In the sense that as they are ill-conditioned or they are unstable with respect to perturbations in the data, which is very important in data science. And probably I'll shift to, mag-shift ako sa notes. I might be writing something. Ba't ako sa meetings? Paano ako makakabalik yun? Yeah, let's go back to the notes and see what's here. Saka para makapagsulat din ako ng content. Okay. Now, in real life, all right. So the scenario is we're using matrices in order to get, say, a set of parameters for a certain data set that we have. So we're solving AX equals B. So it really depends on, of course, a guess of how the parameters are related to the data, and that is encoded in the matrix A, which we now can handle whatever the size is, whether it's invertible or not. Meron na tayong solution doon. The other wildcard here is the right-hand side, B, which could be something that is collected data, right? So kung nagbibilang ka ng tao, you're counting things, then B could be good. If it's a categorical data, that's fine. But if it's a real data, I mean, if it's a measure, so for instance, you want to model, say, the tables here in this conference room, magme-measure ka ngayon ng kanilang length. Now, once you use a ruler or a yardstick or whatever, meron kang value na makukuha. Say, this is about, say, siguro, halimbawa, kunwari lang, this is 1 meter. But essentially, it's not perfectly 1 meter. Yun lang yung sinabi ng iyong measuring device. Pero the actual measurement is not exactly 1 meter. It could be 1.00005 meters, but essentially, hindi siya exact. And that's usually the problem whenever you're collecting data that is measured. Yung hindi ka lang nagkaka. So, lagi tayong vulnerable dun sa mga measurement data, right? And then the thing is, may mga matrices na napaka-sensitive sa right-hand side data. I mean, instead of solving AX equals B, this is the ideal system that we want to solve. But if B is measured in real life, then you are not solving AX equals B. You'll be getting like AX equals B plus some epsilon, where epsilon represents the noise or the measurement error, right? And there's no way in the real world how we can take away the noise. Kasi hindi natin alam kung ano yung noise, gaano siya kalaki. We know it's a small number or it is a small vector, but we don't know exactly what it is. So instead na i-solve yung ideal system na AX equals B, ang kailangan natin i-solve ay AX equals B plus epsilon. And if epsilon is small, we want the solution to AX equals B plus epsilon to be close to the solution of AX equals B, right? And it kind of makes sense, right? Kapag ka meron kang Pag meron kang AX equals B, right? Tapos meron kang AX equals B plus epsilon, where the norm of epsilon is very small, right? It's much, much less than 1, right? Halimbawa sa AX equals B, nakakuha ka ng solution na X star, right? And this is the ideal solution. Now, wala kang access sa perfect data. Some data na meron ka ay B plus epsilon. Now, if epsilon is very small, we expect that the solution we get, say, tawagin nating X tilde, right? So kung maliit si epsilon, gusto ko yung X tilde malapit sa X star, right? And it seems that that is the case, right? We expect that to be the case kasi konti lang naman yung nabago sa right-hand side. So dapat, yung mababago sa solution X star papunta kay X tilde ay maliit din, right? We expect it to be very small, but in some cases, that is not the case. And those matrices that makes that anomaly happen ay tinatawag ng mga ill-conditioned matrices. And we need to be extra careful whenever dealing with ill-conditioned matrices. And unfortunately, ang mga matrices na nagmumula sa inverse problems like parameter search, which is very prevalent in data science, are ill-conditioned. Kaya almost always, hindi mo lang isosolve yung linear system. You need to take into account the stability of the solution. Right? Na at the back of your mind, hindi perfect yung data ko. So, kailangan kong magdagdag ng additional layer to my solution so that the solution I get from the noisy data, which we call X tilde, will be very, very close or will be reasonably close to the actual solution of the system I'm looking for, right? Kasi halimbawa, dun sa analogy natin kanina na medical application. So, nag-blood test ka, nag-blood chem ka, nagpa-MRI ka. So, meron siyang measurement ang binigay. Ito yung right-hand side B mo, ha? Tapos, isolve yung AX equals B para malaman mo kung saan kita tuturukan. Pero dahil dumaan sa MRI yon, may mga measurements involved, hindi AX equals B. Hindi eksaktong B yung binigay sa'yo nung lab test. Ang binigay sa'yo ay B plus epsilon. Pag yung X tilde ay malayo sa X star, lagot ka na kasi baka sa mali ka maturukan. Or worse, kung ang sinusolve mo pala ay kung saan yung initial incision operation. So lalaki yung sugat mo. No? So parang ganun yung nangyari. So you need to be very careful whenever dealing with measured data, right? And the answer to that is regularization. Or one way to deal with that is to regularize the solution. Well, let's see an example here. Yeah. So we want the residual or the difference between the actual solution and the noisy solution to be very, very small. Right? Ang threshold, walang definite threshold ulit, pero we want this to be proportional or to be within the same order as the size of epsilon. Kung 1% yung size ng noise, kung yung magnitude ni epsilon divided by magnitude ni right-hand side B ay halimbawa 1%. Gusto natin yung relative difference between the actual solution and the noisy solution. We want this to be around the same magnitude. Gusto ko siya ay below 10%. Kung 1% yung error, so sige, 1 to 10% error, papayag ako. Huwag sana siya mag-with 100% error. Kasi that's another order. Second order na yun, right? So you want to keep it around the same level. Pwedeng multiple, pero not that much, right? So yun yung titingnan natin. Well, there's a nice measure. How can we anticipate such thing to happen? And that is via solving the condition number ng matrix A. The condition number of the matrix A, maraming definition ng condition number, but this is what I want to use. Yung condition number ni A, denoted by kappa of A, ay yung L2 norm ni A times L2 norm. Actually, in general, ito yung mga condition numbers. Pero pag in-implement ko siya kay MATLAB, ang gusto kong gamitan ay L2 norm ng matrix A times L2 norm ng pseudo-inverse. Yung product na yon, yun yung condition number. At gusto ko ang condition number ay maliit. Pag malaki yung condition number, mahirap gamitan yung matrix, especially on computing devices. Kasi pag nag-truncate ka kahit ng 16th decimal digit, baka malaki yung epekto niya sa calculation. So ito yung mga tinitingnan sa numerical analysis. So ayaw mo na magtiwala sa sagot mula sa computers kapag ang laki ng condition number ng isang matrix A. Right? Why? Because it established na yung relative difference between the actual and the noisy solution ay proportional or is bounded above by a factor of the condition number and the size of the noise. So again, ito yung relative difference. Ilang percent yung layo no noisy solution mula dun sa actual solution. Siya ay bounded above by the condition number times the size of the noise with respect to the actual right-hand side. So ilang percent yung laki ni noise with respect dun sa right-hand side, i-multiply mo pa yon ng cutoff A. Right? Now, to illustrate this phenomenon, balikan natin yung system natin, ay yung matrix natin kanina. 0.15, 0.1, 0.16, 0.1, 2.0, 2.1. And let me do this in MATLAB. Ipat ako. Kaya lang, yeah. Hirap, wala akong tech person. Ako rin yung tech person. Okay. So, yeah. Okay. Students. Yeah, what happened? Okay, let me reshare my screen. There we go. Okay. So, ito yung, babalik ko lang yung matrix A kanina. So, gusto ko siyang i-comment. Tapos yung naka-comment kanina, pwede ko siyang i-uncomment by clicking this. Malabo na pala. By clicking yung percent tapos may X. So, para matanggal yung comment. So, para siya na yung gagamitin ko ulit ng matrix A, right? So, let me just evaluate this selection. So, yan yung selection. And then, again, ano ang solution natin dito? Sige, i-run ko na yung pala yung buong code. F5, F5 ako. So, solution ay 1-1. Right? So, 1-1 yung unique solution. So, remember that, 1-1 yung actual solution. So, ngayon, ang gagawin ko, titingnan ko ngayon, ano yung mangyayari kapag ka nag-introduce ako ng noise. Okay. Diba? Ito yung noise na idadagdag ko. So, copy-paste ko siya dito. So, maglalagay ako ng noise. Ito, kunwari ang measurement noise, but in real life, you don't have access to this. So, minomodel lang natin siya by a random number. So, na ina-add or sin-subtract doon sa right-hand side. Halimbawa, noise ay 0.1, minus 0.032, saka 0.01. So, let me just run this so that pumasok siya sa workspace. Yan yung epsilon. Now, to know how big epsilon is, so you take the norm of epsilon or eps. Eps yung tawag ko dun sa noise, divided by the norm of B. Okay. So that's 0.0105. So ito yung relative size of noise. So yung size ng vector epsilon, ng noise vector eps natin ay 1% lamang, around 1% lamang nung vector B. So you can think of it as unliit na error. 1% lang yung error na madadagdag o yung noise, right? Pero tingnan niyo yung mangyayari. Gagawin ko rito yung B, okay? Yung B, papalitan ko ng B plus epsilon. Okay? Kasi nga, hindi ko na measure na eksaktong B. Ang data na pumasok sa akin ay yung B plus epsilon. Right? Tapos, tawagin ko tong X noise. So si X star nakasave pa rin dun sa workspace, hindi ako nag-clear. So 1-1, para lang may reference tayo mamaya. No? Tapos gawin ko tong X noise. So X noise kasi siya yung solution mula sa noisy data. Gagawin ko yung A/B. Pero pag nirun ko tong buong code, yung B mapapalitan na ng B plus epsilon. So makukuha ko na ay noisy right-hand side. So if I press F5, okay, makikita nyo yung solution na nakuha ko. X noise is negative 2.99 tapos 7.8. 2179. Right? Na napakalayo dun sa, ano yung solution na alam natin? 1, 1. Right? So pag kukunin niyo yung relative difference, tingnan niyo ilang percent yung error or yung layo. So kunin mo yung norm ng X noise minus X star. Just make sure hindi kayo nag-clear para yung X star nasa workspace pa. Divided by norm ng X star. Okay. 5.2270. So ibig sabihin 500% yung layo ng noisy solution mula dun sa actual solution. Right? So dun nga. Dun ka daw dapat turukan sa 1-1. Pero pag sinolve mo using noisy data, dun ka matuturukan sa X noise which is minus 2.99, 7.21. Super layo na nun, ano? Kung operasyon yan, ang layo na nung sugat, ano? So dadami yung scar. But anyway, that's how far it is. So the 1% noise in the data caused 500% error in the solution that we got, which seems to be very disproportionate. Ano? Ang liit lang nung nabago sa right-hand side, pero 500% yung nakuha kong bagong solution, which doesn't make any sense. Kasi yung konting pagbabago sa, magkamukha pa rin yung dalawang system kung sinolve, pero super magkalayo yung solution nila. And the answer is, ang laki kasi ng condition number ni A. If you want to look at the condition number of A, cont of A, okay, MATLAB, it will give you 629.5801. And remember, what does the condition, ano yung relation ni condition number dun sa relative difference? If you go back to the handout, yung relative difference between the noisy and the actual solution is less than or equals sa condition number sa kappa of A times size ni epsilon over size ni B. Ang size ni epsilon is about 1%. Ang condition number ay 629.58. So, na-expect mo na dapat na yung relative difference is bounded above by 6.29 or somewhere near 6.29. Ano yung nakuha natin na relative change? 5.22, which falls under that bound as it should be. Otherwise, mali pala yung theorem. Ano? Pero dapat na-expect mo na pwedeng pumalo ng 6.29 or 6.30 yung relative difference. So you should be extra careful in getting the solution, right? If you're not worried about these things, ano, you might be misled by the unstable solution. Because if you look at if you look at the norm ng residual, A times X noise divided by B, divided by the norm of B. Sorry. A times X noise minus B divided by the norm of B. This will be about 0.0056. So, ibig sabihin nito, na-approximate ng maayos ni X noise yung solution. Because the relative error is just 0.56%. But the interpretation there is, anong sinolve natin dito? Yung noisy system. Right? So, ibig sabihin, na-solve ni X noise yung noisy system ng maayos. It has only an error of 0.56%. So, na-fit niya yung noisy data. Pero, hindi naman yung noisy data yung hinahanap natin. Ang gusto natin, as much as possible, makuha natin yung sa actual solution. Right? So, kung titingnan nyo yun, norm siya dapat ng A times X noise minus B minus X minus X. Pero what we get here is maayos pa rin yung kanyang pagkaka-approximate dun sa non-noisy data, pero malayo pa rin yung solution. Kasi nga, napakataas ng condition number ni A. Okay? Now, dahil wala ng time, let me just go quickly back to the slides. Kala ko matatapos mo. Sabi ko ngayon, ang bilis lang ng lecture natin. Kasi meron kaming acquaintance party ng 7. Pero sabi niya, hindi na naman ako umabot. Pero just a teaser to what we'll do next time. So nakita natin, ang laki ng error. No? So, pero there's a method that I can drive the relative difference down between the actual solution and the noisy solution. In fact, in my previous simulation, lumiit na to 11% yung difference between the noisy solution and the non-noisy solution. And imagine yung improvement. Kasi kanina, yung noisy solution natin ay 522% kalayo mula dun sa actual solution. But later in the handout, we can get a solution which has only 11%, which is only 11% far off from the actual solution. And the method that we'll use is the L-curve regularization. And that will be our topic for Tuesday of what? For Wednesday next week, right? Pero yung code, yung L-curve code ay na-send ko na dun sa email ko kanina. So we'll play with that code. I'll demonstrate how that is used at i-recreate natin, or we'll try to get something close to what I got in the handout. All right? But that will be for Wednesday. Okay? All right, so we'll end here. Do you guys have any questions, clarifications?
Parang ilan lang yung mga masasabi natin na hindi gaano sensitive yung hindi gaano sensitive yung sa maliit na perturbations.
Probably, again, there's no rule of thumb. Ano, depende sa application from application. Pero if you'll go by what I said na sana, relative difference between the noisy and the actual solution ay maging of the same order as the size of the noise. So, pag sinabi ko same order, same within the factor of 10. Huwag ka mag-multiply ng 10. So, sana nandun pa siya. So, we want more or less the condition number to be less than 10. The ideal is 1. Pero we want it to be between 1 and 10. Siguro, yun na yung pinakamalapit sa rule of thumb na mabibigay ko. Para dun sa inequality, yung relative difference will just be less than or equal sa relative difference naman ng noisy data mula dun sa actual data. Size of the noise divided by the size of P. So, yeah, the ideal is 1. Pero sana siya is something less than 10. So, halimbawa siya is 7. So, ibig sabihin, yung relative difference can be as much as 7 times the error, the size of the noise. Kung may 1% noise ka, yung condition number mo ay 7. So, ibig sabihin yung deviation between the noisy and the actual solution is about 7%, which could be acceptable pa rin. So, yeah, pero for sensitive applications, you still want to drive it, say, to less than, closer and closer to 1. Sana. So, yun yung idea. Right? So, usually si MATLAB hindi siya nagre-reklamo unless yung condition number niya ay pumalo na ng thousands. So, within 10 to the third power. Pagka lumampas na siya ng 10 to the 14th, sasabihin niya, huwag ka na mag-compute. So, lalabas siya ng napakahabang red na error message. Kasi nga, sinasabi niya na huwag mo nang pagtiwalaan yung makukuha kong solution. Kasi computer ako, nagtatrancate ako, malamang kung ganun kalaki yung condition number, you can think of it as kung 10 to the minus 14 yung condition number, ibig sabihin bawal kang magkamali up to the 14th decimal digit. And usually measurement devices cannot do that. Swerte ka na kapag ka plus or minus 5% yung measurement error ng mga medida, mga yardsticks, ano. Pero nagtanong kami sa physicist dati, kasi meron kaming na-derived na method for one application na feeling namin gumagana siya numerically. Pero nung sinasimulate namin siya, dapat tama to the 20th decimal digit lahat ng computations. MATLAB can do that. Sabihan mo siya, okay, huwag ka magta-truncate ng mas malapit sa 20th decimal place. MATLAB can do the computations, pero pag ibebenta na namin siya sa physical application, di na pwede. Kaya sabi ng physicist na nakausap namin, huwag ka nang umasa na may measurement device na accurate to the 10 to the minus 20. Swerte na nga ako maka 5% error kaso that's 10 to the minus 2. Hindi nagagana yung method na. So hindi nagagana yung kapag ka ang condition number ng matrix mo ay more than 100. So parang ganun yung idea. But again, no definite rule of thumb. Okay? Other questions? Yes.
After this section. So yung first part, sir, is yung dito are mga exact measurements.
Yes.
While yung second part is yung mga sensitive na sa measurements na data.
Right.
Okay. Doon sa first part, sir, if our pseudo-inverse is about approximation lang ng inverse, may infinite solution tayo na parameterized by W. Since infinite solution, sir, ano naman sasabi natin na pinaka-magandang solution? If that's the case.
Well, another good question. It depends from solution, from application to application, right? Pero when you're talking about stability, pag stability lang yung pag-usapan natin, we want the smallest solution. Smallest in terms of the magnitude. Yes, yung ipapakita kong L curve, ito try niyang i-minimize yung size ng solution. Kasi yung size ng solution factors in dun sa stability ng solution. Pag masyadong malaki yung X star, pag kinuha mo yung norm ni X star, pag sobrang laki niya, more likely unstable yun. Unstable solution siya. Unstable naman yung solution, hindi yung problem. Kasi yung kanina, yung sensitive sa perturbations, ang unstable doon ay yung problem. Yung solution, may stability rin siya na kanya. Pag malaki yung norm ng solution, unstable siya. So gusto ko as much as possible, sana maliit yung norm ng solution. And luckily, yung L curve na i-discuss natin strikes the balance between the size of the residual. Kasi gusto mo maliit pa rin yung residual eh. Baka naman yung talagang solution niya ay ang laki ng norm. Pero dahil concerned tayo sa uncertainty ng data, baka naman pwede akong mag-give up ng konting residual, tanggapin ko na may, dagdagan ko na konti yung error. Kung ang best solution ay 5% yung error, baka naman acceptable na gawin kong 7% yung error dun sa residual. Pero paliitin ko ng sobra, pero liliit ng sobra yung norm ng solution, which will pay off stability-wise, especially if you do not have perfect data. So yun titingnan natin next time, how to strike the balance between those two, and what's the synergy between the residual and the size of the solution. Kasi nga papasok yun sa question, ang dami pa ng solution eh, sino pipiliin ko? Right? Kung may interpretation ka dun sa solution, well, mas makakapili ka. Halimbawa, sa research namin, yung mga solutions sa mga mga overdetermined systems namin represents the current charges sa isang speaker o sa isang electromagnetic transmitter. Pag kinuha mo yung norm yun ay proportional dun sa power budget na kailangan ng speaker. So pag nag-create kami ng sound, kuripot kami sa kuryente, kukunin namin yung solution na may pinakamababang norm para maliit lang yung voltage o yung current na i-feed namin dun sa speaker. So for us, there are infinitely many solutions or infinitely many near solutions, pero ang pipiliin ko ron yung pinakamaliit yung norm. Not just from the stability point of view, which is important, pero sa physical point of view kasi ang interpretation niya ay power. Gusto ko maliit lang yung power requirement. Kasi baka lumaki yung bill ko sa Meralco and so on. So parang ganun. So application from application pa rin yung tiniting. Alright? So let's talk about that next time. Alright? So meron pa bang burning questions? So pwede na ako mag-party. Alright, so thank you for coming guys. We'll see each other again on Wednesday. Tapusin pa natin tong module na to. Alright?